Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Wormholes. Tunnels through space, time, and beyond. A cosmic longing across the void. The night sky has always beckoned with an impossible promise. Every pinprick of starlight that reaches our eyes has traveled across unfathomable distances, a silent messenger from worlds we can barely imagine. We stand here on our tiny planet, looking up, and feel the gulf that separates us from those distant suns and galaxies. It is a feeling both humbling and haunting, an immense loneliness in the face of a universe so vast. Is there a way across this cosmic ocean? In our hearts, a longing takes shape, a yearning to bridge the unbridgeable, to be everywhere that wonder calls us, and to break the limits imposed by space and time. For as long as humans have dreamed, we have refused to accept isolation in the cosmos. Across cultures and ages, our stories have imagined secret paths and hidden doorways in the sky. Myths spoke of gods racing their chariots through the heavens, of enchanted bridges linking Earth to paradise, of travelers riding moonbeams or rainbow paths from one world to the next. These ancient tales all spring from the same source, the deep human desire to connect, to reach out across distance and find something or someone on the other side. In those imaginings, distance was not a prison, but a challenge to overcome with courage or magic. Today, we no longer ride on mythic chariots pulled by celestial horses. Our vehicles are rockets, and our magic is science. Yet the longing remains. We launch probes to the outer planets. We beam radio signals to the stars, hoping for an answer. Still, the distances are cruel. The nearest star beyond our sun is over 4 light years away. Even a message traveling at light speed takes years to get there, and a human spacecraft would require tens of thousands of years. The scale of the universe threatens to keep us forever apart from the wonders we yearn to touch. But what if there is a back door? What if space itself has hidden tunnels, shortcuts that cheat distance and time? What if the universe in all its vastness has secret pathways known as wormholes? In this journey, we will venture into that bold idea. We will follow the path from the dreams of ancient skyfarers to the cutting-edge theories of modern physics. We will step through the looking glass of general relativity and quantum mechanics, peering into the enigmatic tunnels that might bind distant galaxies or even separate universes. Along the way, science will mingle with imagination. We will grapple with equations silently, absorbing their implications without writing them down, translating them into visions and metaphors. We will confront paradoxes of time travel and questions that test the limits of reality. And through it all, a poetic thread will guide us. The voice of our collective awe and wonder, a conversation with the cosmos itself. Picture, for a moment, standing before a shimmering portal in space. On this side, the familiar night sky, the Milky Way's band of stars arcing overhead. On the other side of the portal, seen faintly through its depths, a different sky, perhaps alien constellations or the glowing swirls of a nebula that should be thousands of light years away. Step forward, and in an instant you might emerge there, your foot finding ground under an alien sun. This is the tantalizing promise of a wormhole, a bridge that can unite 2 far-flung corners of the universe as though they were next-door neighbors. It sounds like fantasy, and it may well be. No one has ever seen a wormhole, and they might not even exist. Yet they are permitted by the known laws of physics. In the mathematics of Einstein's theory of gravity, wormholes appear as possible solutions, theoretical tunnels through space-time that could, in principle, connect regions that would otherwise be forever separate. They sit at the edge of our understanding, like whispers from a higher reality. Some scientists believe that if certain extreme conditions could be met, A wormhole might be held open long enough for something or someone to travel through it. Others are skeptical, suspecting that nature has subtle rules, cosmic censorship, some call it, or chronology protection, that forbid such audacity. We do not know the answer, not yet. And yet, the quest continues. Why? Because the stakes are so alluring. A traversable wormhole, if one could be made real, would rewrite the geography of the cosmos. Distance would lose its tyranny. The light years between here and the galactic center, or between our galaxy and Andromeda, would become irrelevant, mere steps through a cosmic doorway. We could visit other star systems not in generations or millennia, but perhaps in a single lifetime, maybe even instantaneously. More profoundly, wormholes tug at the threads of reality in ways that challenge our understanding of cause and effect, space and time. They raise the prospect of time travel, journeys to the past or future, and the mind-bending paradoxes that come with them. They force us to confront whether the universe has an underlying web of connections that we are only beginning to sense, connections that might tie together not just where we are, but when we are, and even what universe we inhabit. So let us surrender to curiosity and wonder. Let the scientific rigor be our compass and poetic imagination our sail. Together, we will explore the story of wormholes, from their first glimmers in Einstein's equations to the latest ideas in quantum physics and string theory, from the challenges of keeping such a tunnel open to the tantalizing hints of how we might detect one out in the starry night. We will ponder what it would feel like to step through a wormhole and emerge light years away. We will wrestle with time loops and parallel universes and ask what all this means for us. Fragile beings who love, hope, and dream. By the end, we'll return to that human longing which set us on this path and reflect on how even the act of imagining these cosmic bridges speaks to something timeless within us. Our journey begins where humanity's fascination with bridging the heavens first took root, in the stories and early theories that tried to break the walls of distance. We leave the comfort of the known shore and push off into the cosmic ocean, hearts full of yearning, eyes open in wonder, asking, are the stars as unreachable as they seem, or has nature hidden a shortcut among them? The dream of bridging space and time. Long before wormholes had a name, the idea of traversing the sky in the blink of an eye lived in human imagination. The ancients stared at the same stars we do, but in their minds, those points of light were not unreachable. They were destinations for heroes and gods. In myth and legend, distance was malleable. A hero might be gifted a pair of winged sandals or a flying horse to vault from one world to another. A deity might descend to earth on a rope of light or a rainbow bridge. Consider the old Norse tales of the Bifrost, a shimmering rainbow said to connect the mortal world of Midgard to Asgard, realm of the gods. Or the Hindu epics describing magical chariots, vimanas, that could soar through the sky and even visit the stars. These were early expressions of a dream, to break the barrier between here and there, to travel without traversing the immense gulf in between. Such stories may seem far from scientific truth, yet they reveal something fundamental about us. We have always been storytellers, trying to shrink the darkness between distant points of light into something we can cross. The dream of instantaneous travel, of portals and shortcuts, is a recurring theme. We whispered it in our fables and wrote it into our fiction as soon as we had the language of science. When technology advanced and we began to grasp the true scale of space, our fantasies did not die. They adapted. In the late 19th and early 20th centuries, writers like H.G. Wells imagined doors in space and time, in tales of time machines and journeys to other worlds, even as scientists were uncovering the real, mind-bending properties of the physical universe. Then came a revolution in our understanding of reality. In the early 20th century, Albert Einstein upended the old, common-sense notions of space and time. His theory of general relativity revealed that space and time are not static, separate backdrops, but a unified, dynamic fabric, space-time. Massive objects like stars and planets curve this fabric, and what we feel as gravity is just objects moving along the curves. Space could stretch, squeeze, and even rip under extreme conditions. Suddenly, the idea of cosmic shortcuts didn't seem entirely absurd. Space-time itself could bend, so perhaps it could bend enough to fold distant points together. Einstein's equations were complex and rich with possibilities. Even Einstein himself did not immediately grasp all the strange implications of his theory. But soon, others began to explore his equations for hidden pathways. One of the first was an astronomer and war hero turned physicist, Carl Schwarzschild. In 1916, while Einstein's work was still new, Schwarzschild found a solution to the equations that described the spacetime around a very compact mass. This was essentially the first theoretical description of a black hole, an object so dense that it creates a deep well in spacetime, a gravity pit from which not even light can escape. At the center of this theoretical black hole was a point of infinite density, a singularity, where the known laws of physics would break down. To Schwarzschild and others, these results were mathematical curiosities. Black holes seemed like an extreme, almost inconceivable outcome. Who could imagine a star collapsing so completely that it punches a hole in the fabric of reality? It took decades for physicists to accept that black holes might actually exist in nature. Yet, hidden in Schwarzschild's solution was something even more fantastical than a black hole. If you extended the mathematics a bit further, you found a strange possibility. Schwarzschild's metric hinted at a tunnel-like structure. In the purely mathematical sense, it was as if the equations allowed the hole to connect to another opening somewhere else. A bit like a tunnel with two mouths, one at each mouth looking much like a black hole from the outside. This was the first glimpse of what we now call a wormhole. In 1935, Einstein himself, along with his colleague Nathan Rosen, took these ideas seriously. They published a paper exploring the idea of bridges in space-time, solutions that connected two regions of space. These came to be known as Einstein-Rosen bridges, essentially wormholes by another name. To visualize it, think of space-time as a great sheet or canvas. Place two distant points on the sheet, say, two stars far apart. Normally, the only way to travel between them is to traverse the sheet, moving through every intervening point. That's a journey that could take thousands of years. But now, imagine pulling those 2 points together, bending the sheet so that they touch, and poking a hole that goes directly from one to the other. The result is a tunnel that bypasses the usual route, a wormhole. Einstein and Rosen's work suggested that under certain conditions, space-time could form such a tunnel. It was a breathtaking concept. Nature might permit a bridge connecting two separate locations, a bit like a shortcut through a higher dimension. One way to picture it is to imagine space as the skin of an apple. An ant crawling across the surface has to go around the apple's curvature to get from one side to the opposite. But a worm burrowing through the apple can take a more direct route, tunneling a hole that opens up far away on the surface. For the worm, the journey is much shorter than the ant's. By analogy, a wormhole is a tunnel through the apple of space-time, potentially allowing something to travel far in a shorter time than it would take going through normal space. However, Einstein and Rosen's theoretical bridge was not a traversable road for travelers. It was more like a precarious tunnel that closes before anything can pass through. Their solution turned out to describe a wormhole that exists only in a fleeting moment of time. It pinches off too quickly. Moreover, it appeared to connect two regions that each looked like a black hole. In fact, what their math really described was an idealized model of an eternal black hole. A black hole that, in theory, connects to a mirror image white hole in another universe or a distant part of this universe. The white hole would be the reverse of a black hole. Instead of pulling things in, it would only spit things out. The Einstein-Rosen bridge connects the black hole and white hole, but unfortunately, it's not the kind of bridge you'd actually want to step onto. If you tried, you'd be crushed by the tremendous gravity at the entrance, and even if you somehow avoided that, the tunnel would pinch shut and you'd be trapped or destroyed as it collapsed. So, in those early years, wormholes were a tantalizing idea, but they seemed to be a cosmic tease, allowed by the mathematics but naturally unstable and untraversable. To the physicists of the time, they were interesting mathematical artifacts more than anything. Einstein reportedly thought of this bridge concept as a way to model fundamental particles, like electrons, as maybe one end of a tiny wormhole whose other end was some other particle, thereby eliminating singularities. It was a clever idea on paper, but it didn't bear out in reality. And so, for a time, wormholes remained in the shadows of theoretical physics. They made occasional appearances in science fiction as a convenient plot device. Long before the term wormhole was even coined, novelists had imagined doorways through space. But serious science had set them aside as nothing more than quirks of general relativity's equations. Yet the seed was planted. The notion that our universe might have hidden passageways was too fascinating to disappear entirely. It slumbered, quietly residing in the equations and in the back of physicists' minds. As decades passed, humanity achieved something once reserved for myth. We began actual space travel, though on a very local scale. We sent rockets to orbit Earth, then astronauts to the moon. Probes flew outward to our neighboring planets. Each step made the vast distances of space a bit more concrete, and perhaps more daunting. The nearest stars still lay far beyond reach with any technology we could foresee. It was against this backdrop that the wormhole idea was destined to re-emerge, no longer just as a trivial math oddity, but as a serious proposal intertwined with some of the biggest questions in physics. Einstein-Rosen bridges and beyond. By the mid-20th century, the word wormhole had been coined, likely by physicist John Wheeler in the 1950s, to give a catchy name to these hypothetical tunnels. The name itself evokes something crawling through an apple or the earth, making a hidden shortcut. Wormholes moved from obscure journals into mainstream imagination. Still, for a while, they were mostly considered science fiction or extremely speculative science. After all, if Einstein and Rosen's version collapsed instantly, was there any hope of a real crossable wormhole? The next chapter in the wormhole saga came from asking a bold question. What would it take to make a wormhole traversable? If the equations say the tunnel collapses too quickly, is there anything in physics that could hold it open? This line of inquiry took off in the 1980s, led by a few visionary theorists. Imagine you are an engineer of the universe, trying to shore up the walls of a cosmic tunnel so that it doesn't cave in. What kind of scaffolding or material could you use to keep a wormhole stable? This is where things get truly exotic. The answer that general relativity gives is shocking. You would need negative energy or negative mass. In everyday life, we never encounter negative mass. There is nothing you can hold in your hand that weighs 1 kilogram. All masses and energies we know are positive, which produce gravity that pulls inward. But a wormhole's throat, the tube connecting its mouths, naturally wants to pinch closed under its own gravity, much like a heavy tunnel might collapse under its weight. To hold it open, you'd need something that pushes outward against gravity, repulsive gravity, in effect. And that's what negative energy does. It's like gravity with an opposite sign, a sort of anti-gravity pressure. Now, classical physics insists that energy is always positive. You can remove energy from a region, make it cold or empty, but you can't have less than 0 total energy in it. However, quantum physics, the physics of the very small, has some loopholes. In the quantum realm, particles and antiparticles can spontaneously appear out of nothing as long as they vanish quickly. The energy accounting can momentarily go negative in small regions due to the uncertainty principle. There is also a phenomenon called the Casimir effect, where two metallic plates placed extremely close together in a vacuum will actually feel an attractive force due to quantum fluctuations of the electromagnetic field. In between the plates, certain energy modes are suppressed, effectively creating a region of lower than normal vacuum energy. You could call it a pocket of negative energy density relative to normal, empty space. When scientists observed the Casimir effect, they essentially glimpsed a tiny fragment of this exotic stuff that the wormhole theorists were talking about: negative energy. In the 1980s, physicist Kip Thorne and his colleagues, inspired, intriguingly, by a request from Carl Sagan, who was writing a science fiction novel and wanted to make wormhole travel sound plausible, worked out the first self-consistent theory of a traversable wormhole. They wrote down a mathematical description of a wormhole that a human could, in principle, travel through without dying. No crushing singularities, no instantaneous collapse. It was like designing a tunnel through space-time that was as gentle as possible, a sort of U-shaped tube connecting two faraway locations with no deadly forces inside. The catch? Their wormhole model required threading the throat of the wormhole with exotic matter, matter that has negative energy density. In their calculations, the walls of the wormhole tunnel must be filled with something that has an anti-gravitational effect to hold the tunnel open against the natural tendency to collapse. This was a remarkable insight. It connected wormholes to quantum physics and even to speculative ideas about future technology. If some advanced civilization could somehow gather or generate enough negative energy, they might create or stabilize a wormhole. But generating negative energy in sizable quantities is not something our current science knows how to do. The Casimir effect produces only tiny amounts on tiny scales. For a wormhole large enough for a person or a spaceship, the amount of negative energy needed is beyond enormous. It's something for which we have no mechanism. Nature, however, might have its own mechanisms. Some physicists mused that maybe in the early universe, when conditions were extreme, wormholes could have formed with the help of quantum fluctuations, and perhaps some survived. Or maybe some weird astrophysical object could provide the needed physics. For example, certain hypothetical particles or fields might generate negative pressure. Let's pause and digest what this means. By the late 20th century, the idea of wormholes had evolved from a collapsing Einstein-Rosen bridge to the concept of a traversable shortcut sustained by exotic matter. The science community recognized that nothing in the laws of physics outright forbids wormholes. General relativity permits them, and quantum physics provides loopholes to feed them negative energy. However, not forbidden is far from actually real. There were still many puzzles. Could the required negative energy exist in large, sustained amounts? Would quantum effects somehow always balance out so that you can't get enough negative energy in one place without something going wrong? Some research suggested that nature imposes quantum inequalities, limits on how much negative energy you can have and for how long, which might slam the door on making a traversable wormhole, or at least make it extremely difficult. Despite these unknowns, wormholes had transitioned from myth to mathematics to a full-fledged topic of theoretical research. And as our understanding deepened, wormholes became entwined with other profound ideas. They weren't just about fast travel. They started cropping up in discussions about time travel, quantum mechanics, and even the fundamental structure of reality. To see how, we need to delve into what passing through a wormhole might entail and the strange possibilities it opens up. The traversability problem, holding a wormhole open. To truly appreciate the challenge of traversing a wormhole, imagine trying to walk through a tunnel made of rubber that is under tension, trying to snap shut. Each step you take, the tunnel narrows behind you, eager to pinch off. This is essentially what space-time itself would do to any naive wormhole. Gravity pulls the walls of the tunnel together with overwhelming force. Without intervention, the wormhole collapses so quickly that even a ray of light wouldn't make it through from one end to the other. So, what do we need to keep it open? We introduced the idea of exotic matter with negative energy as the hero of this story. But can we be a bit more concrete about it? What does negative energy even mean? One way to think of it is to consider gravity again. Positive mass energy curves space-time in a way that attracts. Negative mass energy, if it existed, would curve space-time the opposite way. Its gravity would repel. If you had a lump of negative mass and you put a normal object near it, the normal object would feel a repulsive force pushing it away. And interestingly, the negative mass would seem to chase the normal mass, a strange quirk of the equations. This kind of material isn't known to exist in any tangible form. But in the wormhole context, we don't need a chunk of negative mass metal or anything. We just need a region where, effectively, the gravitational field is pushing outward instead of pulling inward. The calculations by Thorne and others gave a prescription. Line the throat of the wormhole with a shell of negative energy density. Think of it like reinforcing a tunnel with steel beams, except here, the beams are made of something that creates anti-gravity. This would push outwards on the tunnel walls and keep them apart, preventing collapse. How might one obtain such negative energy? Quantum theory offers some ideas. The Casimir effect, as mentioned, is one concrete example. It creates a tiny region of space where the energy density is lower than the space outside. In effect, it's a negative energy pocket relative to the outside vacuum. Another idea comes from the concept of vacuum energy in cosmology, the energy of empty space that drives the expansion of the universe. If one could manipulate the vacuum energy, maybe it could be made negative in some region. Yet another exotic concept is so-called phantom energy, a hypothetical form of energy in cosmological models that has even more intense properties than dark energy and could violate energy conditions, though this is highly speculative. All of this remains theoretical. To date, we humans have not created negative energy beyond the microscopically small Casimir regions, nor have we found negative mass particles zipping around. But in the realm of theory, some interesting developments have occurred. Physicists have crafted examples, mathematical models, of traversable wormholes that obey as many known laws as possible. For instance, recent studies showed that if you have a black hole with a very strong magnetic charge, it might induce quantum effects that effectively generate negative energy in its vicinity. In one proposal, certain kinds of charged, massless particles in a specific quantum configuration could circulate and create regions of negative vacuum energy, thereby propping open a wormhole. These wormholes, however, turned out to be tiny, like subatomic size, essentially useless for humans, but fascinating as a proof of concept that wormholes might not be totally forbidden. Another line of thought involves extra dimensions, which we will discuss more later. If our universe has hidden dimensions beyond the familiar three of space and one of time, those extra dimensions might allow shortcuts or provide the conditions needed for wormholes without having to violate energy conditions in the traditional way. In some brain world scenarios, where our universe is like a membrane within a higher dimensional space, gravity leaks off our brain into the higher dimensions. This leakage might allow for natural wormholes, or at least less stringent requirements for negative energy, because the geometry of space-time could be different than we expect when it's embedded in a larger reality. Imagine our 3D space is like a sheet of paper, and a wormhole is like a fold that goes into the third dimension, height, to connect distant points on the sheet. If you actually had that third dimension to use, which we normally don't feel in daily life, then maybe forming a stable tube is easier. Even with all these clever ideas, one truth remains. If wormholes exist or can be made, they are not easy things. The universe does not hand out faster-than-light cosmic subway tunnels to just anyone. You have to pay in weird, rare currency, negative energy. And perhaps there are hidden costs we haven't discovered yet. Stephen Hawking, for instance, suspected a kind of cosmic self-consistency. He formulated a chronology protection conjecture, arguing that physics might conspire to prevent macroscopic time travel, which wormholes could enable, because any attempt might blow up the wormhole or otherwise thwart the scenario. More on time paradoxes soon. To step through a wormhole safely, you need not only to hold it open, but also to make sure that tidal forces, the differences in gravity that can stretch and squeeze, are not fatal. If you've heard of how falling into a black hole might spaghettify an object, stretching it into a long strand, that's due to intense tidal forces near the singularity. A well-designed traversable wormhole would have to avoid such deadly gradients. In principle, if the wormhole is large enough and the gravity at the throat is not extreme, a traveler might not feel anything more than weightlessness as they drift through. But if the wormhole mouth is small, approaching it would be like approaching a black hole. The gravity might increase sharply, giving you a wild and possibly lethal ride. In summary, the traversability problem forced physicists to think outside the box of normal matter and energy. It took the discussion from wormholes are mathematically possible but useless to wormholes might be made usable if exotic physics comes into play. This was a huge shift. It turned wormholes into something one could, in theory, engineer, given sufficiently advanced technology or understanding of quantum gravity. It opened a door, albeit a very speculative one, to imagining actual journeys through a wormhole. And that invites the question, what would such a journey be like? Before we address the experiential side, let's consider how far we've come. We started with human longing, passed through myths, saw how Einstein's theory gave birth to the idea of wormholes, and confronted the fact that they tend to collapse. We introduced exotic matter as a lifeline to hold a wormhole open. The stage is set. Now, let's step through that stage into the hypothetical reality on the other side of an open wormhole. In the next section, we'll leave equations aside for a moment and engage in a thought experiment. If a traversable wormhole existed, how would it look and feel to those who approach it and pass through it? Inside the cosmic tunnel, anatomy of a traversable wormhole. Imagine you are an intrepid explorer in a future where humanity has managed, against the odds, to stabilize a wormhole. Perhaps it was found naturally adrift in space, a relic of the early universe that we managed to tame with technology. Or perhaps it was manufactured through processes that today we can only dream about. Either way, you are now in a spacecraft approaching one mouth of this wormhole. What do you see? From a distance, the wormhole mouth might resemble a black hole. It could appear as a dark, spherical shadow against a backdrop of stars. Around it, you might see a strange distortion of light. Stars behind the wormhole could appear warped into rings or halos due to the gravity of the wormhole lensing the light. In fact, one distinctive signature of a wormhole versus a black hole might be that you could potentially see light coming through it from the other side. Instead of an utterly black silhouette, the wormhole might have a shimmering interior if the far end opens near some bright region like a nebula or a star. Some theoretical models suggest a wormhole could produce a double image or a ring of whatever lies on the other side. As you draw nearer, the view gets stranger. The star field ahead might start to duplicate or warp radically. Imagine looking straight into the mouth. You could be gazing into a funnel where the far end's environment is visible in a compressed, fisheye view. Around the rim of the mouth, the normal universe's stars might appear smeared into a ring, an Einstein ring effect. It would be as if a piece of another sky is embedded in our space, framed by a gravitational mirage. Your vessel's instruments would note gravitational forces, but if this is a well-behaved wormhole, you don't feel a deadly pull. You carefully align your ship to enter. It's crucial to go right through the center, much like threading the eye of a needle in 4 dimensions. If you veer too close to the edge, the throat walls, gravity could pull you against them and crush you. But let's assume expert navigation. Crossing the threshold of the wormhole mouth, you might not feel anything particularly special at that exact crossing. There's no physical gate or membrane, just a region of intense gravity and exotic effects. Suddenly, the outside universe's view is behind you, perhaps as a pinprick shrinking away. You are now inside the wormhole throat, the tunnel between universes or distant locations. What is it like inside a wormhole? The truth is, we don't know, but we can speculate based on the mathematics of space-time curvature. If the wormhole is large enough, the ride could be surprisingly smooth. You might be in free fall, weightless, not feeling acceleration, much like an astronaut orbiting Earth. The walls of the tunnel are not physical surfaces, but a region of space where curvature is extreme and supported by that exotic matter we discussed. There might be some radiation present, perhaps from particles that wander in or from quantum effects at the throat, so the inside might glow faintly, or it might be dark if nothing is there to emit light. If the wormhole is short, you transit in a flash. For example, you could imagine a wormhole connecting 2 points a few light years apart, but the length of the tunnel itself might only be, say, a few billion kilometers. You might traverse that in a matter of hours at moderate speed, or even minutes if you coast through. In some science fiction, wormholes are depicted as instantaneous teleportation, vanish here, appear there. But a traversable wormhole still has a finite length inside, albeit possibly shorter than the external distance. So you might actually travel through a corridor for a little while. The most mind-bending aspect, however, would be what happens with time and simultaneity. If both ends of the wormhole are stationary, relative to each other, and in shallow gravitational fields, you might not notice anything unusual about time. You leave at 1 o'clock and arrive a little after 1 o'clock because the travel path was so short. But if the wormhole ends are in different gravitational potentials or have been moved around, for example, one end is on a fast-moving spaceship, time could be offset. You might come out and find that clocks on the other side are out of sync with those on the side you entered. This possibility leads to the time travel paradoxes which we will discuss soon. For now, let's focus on the sensory and physical experience. One could imagine looking out the window mid-transit. What would you see? Potentially, you might see the entrance you came from shrinking behind, surrounded by a ring of light from the universe you left. Looking forward, you could see the exit growing, with the target universe's starfield expanding. There might be a region in the middle of the journey where vision is very strange. Some theorists talk about a cavity of highly curved space where light can actually wrap around, and you might see multiple images of anything inside, or even see your own ship's taillights ahead of you, due to light curving around the tunnel and coming back. It could be a visual kaleidoscope, an echo chamber of light. Now imagine the moment of exit. One instant, you're in the tunnel, mostly surrounded by darkness and the memory of the stars you left. The next instant, a whole new vista blossoms before you. It could be startlingly sudden, like stepping out of a cave into daylight. If the wormhole opens near a star, that star's light will flood the tunnel as you come out. If it's in deep space, you might emerge into a view of a galaxy that is oriented completely differently from the one you left. Perhaps you're now thousands of light years away, looking at constellations that are alien to you. You check your navigation instruments and confirm it. You have arrived at the other side of the wormhole. The distance that would have taken an unthinkable journey outside, maybe crossing entire swathes of the galaxy, took only a short passage inside this tunnel. To summarize the anatomy, a wormhole has 2 mouths, also called portals or ends. Each mouth might look like a black hole externally, but without an event horizon trapping you. In a traversable wormhole, effectively, the event horizon is either non-existent or has been altered so you can go both ways. The mouths are connected by a throat, which is the space inside the wormhole. The throat's spatial length can be anything from a tiny distance to arbitrarily long, but for a useful wormhole, we want it short relative to the external separation. The throat must be sustained by some form of exotic structure, negative energy, to prevent collapse. If that sustenance fails, the wormhole could either pinch off, leaving 2 isolated black holes, or 1 black hole and 1 white hole that quickly ejects its content and closes. Or it could violently explode, implode, either way destroying anything inside or at the mouths. In a well-constructed wormhole, tidal forces can be small. That means you wouldn't necessarily be stretched or crushed. It could be like floating in gentle space. However, near the mouths, there could be strong gravity gradients if the mouth is small. What about communication through a wormhole, not just travel? If the wormhole is open, you should be able to send light signals through it. That means you could shine a flashlight into one end and it would emerge out the other, perhaps with some distortion. You could have a conversation with someone on the far side, like a telephone line, by sending light or radio signals back and forth through the tunnel, with effectively no time delay beyond the transit through the throat. If the wormhole is short, that would be nearly instantaneous, even if the mouths are light years apart externally. This raises a profound implication. Wormholes allow information to defy the normal speed of light limit for journeys through space. You still can't send information faster than light through any one region of normal space. But the wormhole provides a shortcut route, so effectively, you beat a beam of light that tries to go the long way outside. Before we get ahead of ourselves, it's worth noting that being inside a wormhole might not be quiet and peaceful. There could be weird radiation. There might be quantum effects like Hawking radiation if the wormhole mouths have some properties akin to black holes. Also, if the wormhole connects very different environments, say one mouth near a star and another in intergalactic space, there could be flows of matter. Gas might be drawn through, or cosmic rays might funnel in. A traveler might see a faint glow, or feel a flux of particles. But let's assume our wormhole is clean and well behaved. Emerging from the wormhole, one also wonders, is the trip one way or can you go back? A traversable wormhole, by definition, should allow two-way travel. That's in contrast to, say, a black hole to white hole connection, where you could only go one direction, into the black hole and out the white hole, never backwards. With exotic matter maintaining the throat, you should be able to reverse course and go back through the wormhole the way you came, effectively returning to your original location and time, depending on circumstances. It would be a round trip shorter than a photon could have done in normal space. What about the edges of the wormhole mouth? If you try to go around a wormhole mouth in normal space, you'd just circumvent it, like going around a spherical mass. There's no event horizon, so you could in theory orbit a traversable wormhole like any massive object. Perhaps one might station a ring-shaped space station around the mouth at a safe distance, acting as a gateway port. People or ships could approach, line up, pass through, and then, on the other side, another station could receive them. It's fun to imagine the engineering. You'd probably mark where the wormhole mouth is in space with beacons, because visually it might be confusing since it distorts light. We've now lived out a small hypothetical, journeying through a wormhole and seeing what it's like. It sounds almost serene in our description, but underlying it is a titanic achievement of physics. To go through a wormhole safely, we essentially had to assume new physics, exotic matter or similar, and an understanding of quantum gravity that we currently lack. We also assumed nothing went terribly wrong, no collapse mid-transit, no violent gravitational spasms. It's clear that wormholes blur the line between science and fiction at this moment. We simply don't know if such an experience will ever be possible. But thinking about it yields insights. For instance, it emphasizes how wormholes allow faster-than-light travel through the shortcut, but not local violation of physics. A person in the tunnel always moves slower than light locally. It also hints at why wormholes might enable time travel, which we should discuss now. We mentioned that if one mouth's clock is out of sync with the other, one could possibly travel not just across space, but across time under certain setups. Let's unpack that next, because it's one of the most paradoxical and profound implications of wormholes. Loops in time, wormholes and time travel paradoxes. Wormholes, if they exist, don't only challenge our notions of distance, they can also shake our understanding of time. We all have an intuitive sense of time's flow. Cause precedes effect. Clocks tick forward uniformly for all, aside from Einstein's known effects of relative motion or gravity. Time travel has long been a staple of science fiction, usually treated as something distinct from space travel. But in relativity, space and time are intertwined. A wormhole is a spatial shortcut, but under relativity, a shortcut in space can become a shortcut in time under certain circumstances. How could a wormhole allow time travel? The key is something called a closed time-like curve, which is a fancy term for a path through space-time that loops back on itself, meaning if you travel along it, you end up at the same point in space and time, effectively returning to your own past. Normally, such loops aren't present, at least at macroscopic scales. In our universe, they are mostly the stuff of thought experiments, but wormholes open the door to them. Here's a thought experiment to illustrate. Suppose we have a traversable wormhole with two ends, A and B. Initially, they are synchronized in time. Clocks at A and B both read, say, 12:00. Now, if nothing else is done, going through the wormhole from A to B is just like stepping through a door. You arrive essentially at the same time you entered, maybe a few minutes later, because you traveled through the tunnel. No time travel yet. However, now let's take end B on a journey. Put the B mouth on a fast-moving spaceship and fly it around at high speed, near the speed of light, or take it on a trip near a strong gravitational field. Then bring it back near A. Einstein's relativity tells us that moving clocks or clocks in deep gravity run slower relative to those that stay put. So when B comes back close to A, its clock might be behind A's clock. Perhaps B's clock now reads 11 o'clock, while A's reads 12 o'clock, meaning B's mouth has experienced time 1 hour less than A's due to time dilation. Yet, because the wormhole connects them, the connection disregards the external time difference. Now what do we have? We have wormhole mouth A at local time 12 o'clock, and wormhole mouth B at local time 11 o'clock from its perspective. If you enter mouth B, the one that experienced less time, at what B considers 11:05, you might come out of mouth A when A's clock says 12:05, but B's 11:05 corresponds to an earlier moment on A's timeline, because B's clock is behind. Essentially, you would emerge from the wormhole at A at a time before you entered B. In other words, you traveled back in time by an hour as measured on A's side. This is tricky to describe without a diagram, but the result is famous. A wormhole whose ends have been moved around relative to each other can become a time machine. You could go through in one direction and come out in the past of where and when you started. If you go the opposite way, from A to B in our scenario, you'd go an hour into the future relative to entrance time. So the wormhole allows an asymmetry. One direction is a trip to the past, the other to the future. What can you do with such a time-traveling wormhole? Theoretically, you could send information or objects to the past. This raises all the classical paradoxes. The grandfather paradox, what if you go back and prevent your own existence? Or the bootstrap paradox, what if you bring back information or an object that has no origin because it was passed from future to past in a loop? Wormholes don't automatically allow unrestricted time travel to any era. They link specific times and places, the times at which the wormhole mouths exist. So, for example, you couldn't use a wormhole created in the year 2200 to go back to 2025 if the wormhole didn't exist in 2025. But you could potentially go back to when it was created or first opened. Physicists have poured a lot of thought into whether these paradoxical situations could actually happen. Some have concluded that any attempt to create a time loop with a wormhole would result in conditions that destroy the wormhole or otherwise prevent the paradox. One idea is that radiation would build up. Imagine a simple scenario. You try to send a bit of light, a photon, through the wormhole to the past. If the alignment is just right, that photon could emerge in the past and potentially do something like nudge a mirror that ensures that same photon ends up going into the wormhole again. Now, if each loop amplifies the number of photons, say it triggers an emission of 2 photons that then go back, You might get an exponential pileup of energy, effectively an infinite feedback loop, as the photon circles through the time loop over and over, all cramming into the same moment. Calculations show that when you approach a configuration where wormholes would allow backwards time travel, these feedback effects can become infinitely large, suggesting the wormhole would get blasted apart by the energy surge. This is related to Hawking's chronology protection idea. Even if physics doesn't explicitly forbid a closed, time-like curve, the universe might protect itself by making the conditions unphysical, like requiring infinite energy, or by destroying the wormhole when it tries to form a time loop. Other physicists argue for consistency. Maybe time travel can happen, but you could never create a paradox because the only histories that survive self-consistently are those where events already account for the time travel. This is known as the Novikov self-consistency principle. In simple terms, if you go back in time, you might become part of history rather than changing it. For instance, you might attempt to prevent an event only to realize that your interference is what caused it, or that something always thwarts your efforts. The timeline would somehow find a way to avoid inconsistency. That's a more philosophical stance and hard to test, but it's not mathematically ruled out in relativity. If wormholes were available to actual beings, the temptation to use them as time machines would be huge. It could be wonderful. Imagine being able to see the past, or send warnings backward, or retrieve lost information. Or catastrophic. Someone could try to tamper with causality, or accidents could spawn loops that we can't foresee. We might have scenarios of multiple timelines or parallel histories if one interprets quantum mechanics that way. Perhaps each paradoxical attempt splits off a new branch of reality, a many-worlds interpretation applied to time travel. So you can't truly change your original world's history. You only create a new, divergent timeline. Alternatively, perhaps any attempt to change the past simply results in the same outcome, keeping the timeline consistent. The ethical and practical implications are enormous. We will talk about ethics soon, but focusing on physics. Wormhole time machines are extremely speculative, but not outright forbidden by general relativity alone. It's quantum mechanics and maybe deeper principles we don't yet know that might intervene. Indeed, many experts suspect that once we have a full theory of quantum gravity, it will show that traversable wormholes or wormhole time machines can't actually form under realistic conditions. Some recent calculations in string theory and other advanced frameworks hint that perhaps traversable wormholes require special setups that aren't naturally occurring or easy to engineer. And even if they exist, maybe they can't be turned into time machines due to subtle quantum effects. Nonetheless, as a thought exercise, wormholes have taught us a lot. They've forced physics to confront what-if scenarios about time travel in a logically rigorous way. The consensus, so far, is if nature allows time loops, it keeps them hidden well. We haven't seen any evidence of tourists from the future or messages from tomorrow, unless one day we realize some phenomenon was exactly that. It could be that wormholes exist, but nature prevents using them to go back before their creation. A kind of limited time travel that doesn't break causality globally, or they might be completely ruled out by something we have yet to discover. Time travel paradoxes make for great storytelling and headache-inducing physics discussions. One famous example often cited: if you have a wormhole time machine, could you go through and shoot your earlier self before you entered, thus preventing yourself from going in? That's a classic paradox. In a consistent universe, something would prevent the situation from happening exactly that way. Perhaps the gun misfires, or you find you simply cannot bring yourself to do it. Or you shoot, but only wound, and end up causing the very scar you saw on your older self that motivated going back. The universe might enforce self-consistency, or timelines might branch into parallel worlds, rather than truly changing a single history. This possibility of parallel worlds brings us to another fascinating lens through which wormholes can be viewed: quantum mechanics and entanglement. It turns out that the equations and concepts that produce wormholes in relativity have surprising analogues in the quantum world, and understanding one could illuminate the other. Invisible bridges, wormholes, and quantum entanglement In the 1930s, the same year Einstein and Rosen published their idea of wormhole bridges, Einstein-Rosen or ER bridges. Einstein was also involved in another famous paper with Podolsky and Rosen on a completely different topic, quantum entanglement, often abbreviated EPR after the authors. Entanglement is the bizarre quantum phenomenon where two or more particles become linked, such that the state of one instantly influences the state of the other, no matter how far apart they are, as if they share a connection outside of normal space. Einstein found this spooky action at a distance deeply unsettling. It took many decades, but experiments repeatedly confirmed that entanglement is a real feature of our world. If you create a pair of photons or electrons in a certain quantum state, then separate them by miles, they behave in ways that defy classical explanation. Measuring one seems to instantly affect the other, in correlation, even though no signal passes between them, at least none that we can detect, and none that obeys normal speed limits. It's as if entangled particles are dancing in unison across any distance, without communicating in the usual sense. For a long time, entanglement was just a quantum oddity, something to be accepted and perhaps harnessed, as we do now in quantum computing and cryptography. But some physicists began to notice a curious resonance between the properties of entanglement and the properties of wormholes. Both seem to suggest some kind of deep connection between distant points. Could these two be facets of the same underlying reality? This line of thought gained momentum in theoretical physics, especially around 2013, when two prominent theorists, Leonard Susskind and Juan Maldacena, boldly conjectured ER equals EPR. In plain language, that proposal suggests each quantum entangled pair of particles may be connected by a tiny Einstein-Rosen wormhole bridge. They didn't mean there's an actual tunnel you could traverse between those particles. These would be extremely tiny and non-traversable wormholes, so you couldn't send a person or even a photon through them. Rather, it was a way to reconcile how entanglement could have such immediate correlations without traditional signaling. Perhaps, in some higher dimensional sense, entangled particles are adjacent, connected by the equivalent of a wormhole that shortcuts through an unseen dimension of space-time. This idea remains theoretical and somewhat speculative, but it has intriguing support in certain advanced theories, like the holographic principle and string theory. For example, in certain simplified universes, toy models that physicists study, like a universe with a negative cosmological constant used in holographic duality, it's been shown that you can have two black holes that share a single interior because they're quantum entangled. That interior is effectively a wormhole linking them. If you have two black holes maximally entangled, it's as though they form a single connected system via an ER bridge. Why does this matter? Because it hints that space-time geometry and quantum entanglement are deeply related. Some even suggest that space-time itself could be woven from quantum entanglement threads. In other words, the unity of space, the fact that space feels like a continuous whole, might arise from the vast network of entanglements between all the microscopic constituents of the universe. If entanglement is like invisible filaments connecting particles, and if each such filament is a tiny wormhole, in a mathematical sense, then our space might literally be the product of these connections. It's a poetic and mind-expanding idea. The fabric of space-time may be stitched together by quantum threads of entanglement, and wormholes are the geometrical picture of those threads. This concept also provides a new way to think about black hole puzzles. There's the famous black hole information paradox. If a black hole gobbles up information, say someone falling in with a diary, what happens to that information when the black hole eventually evaporates via Hawking radiation? Quantum physics says information can't be destroyed, but it seemed like black holes might violate that rule. Some resolutions using the ER equals EPR idea suggest that Hawking radiation particles, the ones that escape a black hole, are entangled with what's inside, and by extension connected via tiny wormholes. So perhaps information isn't lost at all, but rather subtly transferred out through those connections. This is still a hot research area, but it's amazing that wormholes found relevance in it. Additionally, Recent experiments, though very rudimentary, have tried to simulate wormhole-like behavior in quantum systems. In late 2022, a team of physicists reported using Google's Sycamore quantum processor to simulate a tiny wormhole. They engineered a system of entangled quantum bits, qubits, that behaved analogously to two minute black holes connected by a traversable wormhole. By sending a simple message into one side, in the form of quantum information, and seeing it emerge on the other side, they in essence demonstrated teleportation via an entangled wormhole. Of course, no actual space tunnel was formed. It was a mathematical analog within the quantum computer. But this experiment shows that the ER equals EPR idea is more than philosophical. It can inspire real tests that deepen our understanding of quantum gravity, bringing wormholes out of pure speculation and inching them toward empirical science. Stepping back, even if every entangled pair has a wormhole, is too literal a statement. The emerging theme is that space and connectivity might be an emergent phenomenon. The distance between two particles might be partly a function of how entangled, or not entangled, they are with the rest of the world. Perhaps everything in the universe is much closer in some deeper quantum sense. Like pages in a book seem separate in 2D, but are adjacent in 3D when bound together. It's almost philosophical. Maybe what we perceive as empty space between objects is just a manifestation of most things being only weakly entangled. If we could see the true quantum connections, perhaps no two objects are ever truly isolated. In simpler terms, one could say quantum mechanics offers invisible threads, and general relativity offers tunnels, and they might be describing the same phenomenon in different languages. When you marry the two, you get a richer picture where geometry, like wormholes, and quantum connections, entanglement, unify. Understanding this unity might be key to formulating a theory of quantum gravity that so far has eluded science. Furthermore, this interplay between entanglement and wormholes suggests new avenues for experimentation. That recent quantum computer simulation is one example of how these ideas are moving toward the realm of testable science. It was a very toy model of a wormhole, but as quantum technologies improve, we might simulate more complex wormhole scenarios in lab systems, giving us insight into how real wormholes, or the underlying principles, might work. This quantum perspective leads naturally to the idea of extra dimensions and string theory, where wormholes might find a more comfortable home. If entanglement hints at hidden connections, string theory takes it a step further by positing actual hidden dimensions of space in which wormholes could exist. To fully appreciate that, we should step into the world of higher dimensions, a place where our imaginations and equations venture beyond the 4D space-time we directly know. Wormholes and higher dimensions, the string theory view. The concept of wormholes fits intriguingly well with the idea that there may be more dimensions to space than the three we experience. String theory, a leading though unproven framework for a theory of everything, requires extra spatial dimensions. In some versions, as many as 6 or 7 additional dimensions curled up at tiny scales. If these extra dimensions exist, wormholes might be more than just theoretical oddities. They could be natural geometric features that involve those hidden dimensions. Think back to the analogy of a 2D creature on a sheet of paper, for whom a wormhole might just be a mysterious door that teleports them. But in our 3D view, we see it as a tube that goes off the sheet. In the same way, perhaps what looks impossible or singular in our 3D space is easily done by curving through a 4th or 5th spatial dimension. One popular brain world idea, brain meaning a membrane-like universe, is that our entire universe is like a 3-dimensional surface embedded in a higher dimensional space, often called the bulk. In these scenarios, it's been shown that gravity might propagate through the bulk, while light and matter are mostly stuck on the brain, our universe. If gravity can seep out, perhaps it can also find shortcuts. Indeed, some researchers have found that in certain setups like the Randall-Sundrum model, a specific 5D model addressing why gravity is weaker than other forces, you could get stable wormhole solutions without needing exotic matter as weird as in pure 4D relativity. Essentially, the higher dimensional geometry itself does the trick of sneaking around energy condition violations. You might have a wormhole that appears to violate 4D rules, but actually it's perfectly fine in 5D. It's just borrowing an extra dimension to sustain itself. Imagine two distant regions on our brain, our 3D sheet. In normal 3D, they're far apart. But if you can go through the bulk, the higher dimension, maybe they're not so far. Like 2 points on the surface of a table are far in 2D, but a shortcut through the third dimension, above the table, could connect them by a direct straight line through the air. A wormhole might just be a manifestation of our space bending through that bulk to join those points. String theory also introduces new objects, strings and brains, that could potentially form or stabilize wormholes. For example, there are hypothetical entities called D-brains and fundamental strings. One might imagine a configuration where a string or a brain is arranged in such a way as to link 2 points. There is research on D-brain wormholes, where the wormhole is essentially a byproduct of how brains are shaped in higher dimensional space. Another interesting stringy concept is that black holes and wormholes might be closely related through dualities. In certain cases, a wormhole solution in higher dimensions can, when viewed in 4 dimensions, look like a pair of charged black holes or other exotic objects. This is quite technical, but the gist is, higher dimensions open up a whole menagerie of possible shapes and connections for space-time. Wormholes, which in 4D require weird stress energy, might be natural geometric features in 5D or beyond. Thus, discovering a wormhole might indirectly indicate evidence of extra dimensions, a thrilling possibility that would revolutionize physics. There's a more speculative notion still. Wormholes connecting not just different places in our universe, but different universes entirely. In some cosmological models, our Big Bang might have spawned multiple bubble universes, separate regions of space-time that never meet. Usually, each bubble is isolated, but a wormhole could be a tunnel between such otherwise disconnected bubbles. If string theory's picture of a multiverse of brains is true, perhaps one mouth of a wormhole could lie on our brain, our universe, and the other mouth on a neighboring brain universe. That would be literally a portal to another universe. String theory also suggests that at extremely tiny scales, the Planck length, 10⁻35 mem, space-time is not smooth, but frothy or filamentary, echoing Wheeler's quantum foam idea. In that foam, mini wormholes might constantly flicker in and out. Most would be inconsequential, but some theories muse that a few could have been inflated or stabilized somehow. For instance, if a tiny wormhole formed during cosmic inflation, one mouth could have been whisked far away while the other remained near, effectively stretching the wormhole. Or if certain high-energy events, like cosmic string interactions, assuming cosmic strings exist, occurred, they might create small wormholes. If micro-wormholes exist today, they might be all around us at Planck scales, but imperceptible. Some advanced technological civilization, or future humans, might dream of capturing a tiny wormhole and enlarging it, a bit like grabbing a tiny soap bubble and inflating it without popping it. Science fiction as that sounds, it's a scenario that's been contemplated in theoretical papers, using intense fields or special quantum effects to coax a wormhole to grow. So far, string theory and related ideas have not provided definitive, yes, wormholes are real, and here's how to make one, answers. But they have enriched the conversation, showing that under certain conditions, wormholes aren't just mathematical freaks, but plausible structures in a richer cosmic setting. They've tied wormholes to fundamental puzzles like why gravity is weak, maybe because it spreads into extra dimensions, which also allow wormholes. They've linked wormholes to potential signatures like unusual gravitational effects in our 3D world, hinting at hidden dimensions. And if string theory is right about extra dimensions, wormholes might be out there doing subtle things. For example, if gravity can travel through wormholes, two regions connected by one might exert slight anomalous gravitational influence on each other. Some scientists have proposed looking for such anomalies. One idea was that the supermassive black hole in the center of our galaxy could be a wormhole. If so, stars orbiting it might feel tugs from stars or mass on the far side of the wormhole, in whatever region or universe it connects to. As we'll see, people have actually looked at the orbits of stars near our galactic center for unexplained deviations that might hint something invisible is pulling from a mirror world beyond the wormhole. So far, no clear sign, but the fact that we can even make such a test is astonishing. Having journeyed through general relativity, quantum theory, and higher dimensions, you might wonder, are any wormholes actually out there? Or are they all talk and no show? It's a hard question, but scientists have pondered how we might detect a wormhole if one exists in the cosmos. Let's explore what clues we could search for in the sky and whether any hints have turned up. Unstable gateways, tidal forces, and other challenges.
A traversable wormhole, should one ever exist, would be a precarious structure. It's like walking on the knife's edge of physics. One wobble, and the wormhole could collapse or morph into something decidedly non-traversable. We've already mentioned some threats: the requirement of negative energy, the possibility of time travel-induced feedback, etc. Now let's gather those and other challenges to paint a picture of just how delicate a wormhole would be.
1. Tidal forces and gravity, gradients. If a wormhole throat isn't large enough or well constructed, anything entering may be subject to intense tidal forces. For example, if one end of the wormhole is near a massive body and the other is not, the gravity difference can cause huge stresses. Ideally, one might position wormhole mouths far from massive objects to minimize this, e.g. in interstellar space. But even then, near the mouth, space-time curvature is high by definition. That's what bending space into a tunnel entails. If you've got the negative energy balancing things, you might neutralize some of that. But any imperfection could mean one side of your ship feels a slightly different gravitational pull than the other side. And if that difference is too high, it's like the forces near a black hole. You get spaghettified, stretched and squashed. The bigger the wormhole, mouth radius, the gentler the tidal forces can be. So a key engineering goal would be making the wormhole throat as wide as possible for safety. 2. Radiation and vacuum fluctuations. The interior of a wormhole might not be empty. Space is never truly empty. There are always quantum fields fluctuating. In a wormhole, these fields might behave in unusual ways. Some might get blue-shifted, increased in energy, as they travel through the wormhole, especially if one mouth moves relative to the other, as in the time machine scenario. You could have a situation where what starts as harmless vacuum fluctuation becomes high-energy radiation when it emerges out the other end, or bounces back and forth gaining energy. For instance, if one tries to turn a wormhole into a time loop, the vacuum fluctuations looping through might amplify and destroy it, the feedback we discussed with Hawking's idea. Even aside from time loops, cosmic radiation, like high-energy particles, gamma rays, etc., might enter a wormhole mouth. If one mouth is near an active environment, say near a star or a galactic center, and the other mouth is in a quieter region, radiation will pour through from the active side to the quiet side, potentially exposing travelers or equipment to bursts of energetic particles. A stable wormhole might need radiation shielding, or some way to dissipate energy buildup. Perhaps the exotic matter itself helps reflect or absorb it. Otherwise, the interior could heat up or develop dangerous levels of radiation that either collapse the wormhole or harm whatever goes through. 3. Collapse and pinch-off. The exotic matter must be present and arranged just right. If something disturbs it, say it disperses, gets neutralized, or shifts, the wormhole could begin to close. How fast? Possibly at the speed of light or near it. A traveler partway through could be caught as the tunnel pinches down. that might crush or sever them if the collapse is catastrophic. Imagine the throat narrowing like a closing sphincter while you're inside. You might be compressed or stranded in a fragment of space disconnected from both ends. Maintaining the exact conditions for an open throat might be like balancing a pencil on its point, doable with active stabilization, but if your stabilizer fails, down it goes. This is why some theorists suspect traversable wormholes, if they exist, might be extremely transient or require continuous control, like an ongoing application of negative energy from some generator. 4. Quantum instabilities. There are suggestions that wormholes might be inherently prone to quantum instabilities. For example, could they facilitate processes that normally are ultra-rare or forbidden? One wild idea: wormholes could potentially trigger vacuum decay. If our universe's vacuum state is metastable, a possibility in some particle physics models, a wormhole might provide a shortcut for it to decay to a lower energy state, which would be catastrophic. Essentially a bubble of true vacuum expanding at nearly light speed, erasing normal matter and structures. This is very speculative, and most think it unlikely, but it underscores a point. Messing with space-time might have unknown side effects. Even if vacuum decay isn't a concern, wormholes could cause other exotic phenomena like particle production. The strong bending of space might polarize the vacuum and spawn particles, sort of like Hawking radiation. Over time, this could sap energy from the wormhole or flood it with radiation or exotic particles, like an uncontrollable vacuum laser or something. Such issues mean a wormhole might naturally evaporate or shrink as it radiates energy away, unless fed somehow. 5. Interference and interaction with surroundings. Even if a wormhole stands stable in a pristine environment, the universe around it won't stay quiet. It might drift near other masses or be perturbed by passing gravitational waves, like those from distant black hole mergers. Could a strong gravitational wave shake a wormhole and cause oscillations or collapse? Possibly. Wormholes have resonant modes, like any gravitating system. If a wave hits the mouth, the throat might wobble. In a scenario where someone is traversing during such an event, it might be like an earthquake in the tunnel. Also, if humans start using wormholes regularly, there could be traffic management issues. What if too much mass goes through at once? Shoving a huge amount of mass through a wormhole could alter the stress-energy balance and momentarily strain the exotic matter's ability to hold the throat open. Perhaps each transit slightly destabilizes it. You'd need a cool-down period or active damping systems to keep it open after heavy use. 6. Decay over time. Even a theoretically stable wormhole might not be eternal. Maybe it slowly leaks its exotic matter, or quantum effects cause the exotic state to degrade. Over a long time, millions of years, a wormhole could gradually contract or pinch off if not maintained. If civilizations rely on wormholes, they'd have to monitor their health, a kind of infrastructure maintenance. Imagine a far future scenario where a forgotten wormhole network starts collapsing because the generators keeping them open fail. Star systems could become isolated again, or travelers could be lost mid-route. Given all these hazards, any journey through a wormhole would be taken with great caution. It would be like crossing a bridge made of glass over a chasm, hoping it doesn't crack under your weight. One would likely send probes first, measure conditions, possibly actively stabilize the wormhole with some engineered device, like feedback systems injecting bursts of negative energy or adjusting the throat geometry on the fly to counteract perturbations. Perhaps using a wormhole will always remain a delicate operation, not a casual stroll. On the flip side, understanding these challenges is useful. Each of them suggests a way to test or constrain wormholes' existence. For instance, if wormholes tended to collapse with too much mass, maybe none above a certain size could survive, which might tell us why we don't easily see them. Or if they radiate, maybe we could detect an unusual radiation spectrum from what looks like an isolated black hole. So far, We have no direct evidence that any of these speculated issues have manifested in reality. But then, we haven't found a wormhole either. It might be that if nature allows wormholes at all, they exist only in realms we haven't observed, like at Planck scales or in extreme conditions, or are carefully hidden by cosmic censorship of a sort. The bottom line: traversable wormholes would be high-maintenance, temperamental beasts. They're the divas of theoretical physics, requiring special conditions, throwing fits if stressed, possibly self-destructive if you break their rules. But if one could tame such a beast, the rewards are immense. Knowing these caveats, we can now turn our attention to the practical side of things. How might we detect a wormhole if one exists out there in space? After all, it's one thing to theorize and simulate on a quantum computer, but finding a real wormhole would shake the foundations of science. Let's explore what signs or signals a wormhole might give us, and whether scientists have already looked for them. Searching the skies, how could we find a wormhole? Despite wormholes being theoretical, scientists have pondered ways they might reveal themselves if they exist in the universe. After all, if nature did leave a few wormholes around, perhaps formed in the Big Bang or by some exotic process, they might interact with matter and light in noticeable ways. One obvious effect: gravitational lensing. Gravity bends light, as predicted by Einstein and confirmed by many observations, like the famous image of an Einstein ring, where a galaxy's mass distorts the light of a more distant quasar into a ring. A wormhole mouth, having mass and gravity, would also deflect light, but it could do more than a normal mass. Light from a background object could potentially go through the wormhole and come out the other side. So an observer might see weird things, perhaps 2 or more images of a distant star or galaxy, one from light that went the normal long way around, and another from light that detoured through the wormhole. For instance, if a wormhole connected 2 different regions of the universe, we might observe a double image of a celestial object, or an Einstein ring with an unusual shape. Astronomers have actually considered this. They worked out that a traversable wormhole could produce a unique lensing signature, basically a pattern of Einstein rings or arcs that is distinct from what a lone black hole or galaxy would make. One study suggested a wormhole might create 2 concentric rings of light from a single background source, one ring from light that skimmed the outside of the throat, and one from light that passed through and exited the other mouth. Detecting such a double ring would be smoking gun evidence. So far, no confirmed observation of that nature exists, but surveys of gravitational lenses could, in principle, stumble on an odd case that matches a wormhole's fingerprint. Another clue could come from motion of objects near a suspected wormhole. For example, the center of our Milky Way hosts a massive compact object, almost certainly a black hole, Sagittarius A. We have observed stars orbiting extremely fast close in. One idea, put forth by a few researchers, was, what if instead of a black hole, Sag A is actually a wormhole mouth? How could we tell? They proposed that if it's a wormhole connecting 2 places, there might be matter, or stars, on the far side, whose gravity can leak through. That could add a subtle wobble or perturbation in the orbits of stars on our side. Specifically, one study suggested that a star orbiting our galactic center might feel an additional tiny pull, as if there were an unseen mirror star orbiting the wormhole from the other side. If our instruments reached enough precision, we might detect a deviation in the known orbit, which is otherwise explained perfectly by a single central mass. Researchers calculated what sensitivity is needed, and it's extremely high, though future telescopes might approach it. If such an anomaly were found, and other explanations like another small black hole were ruled out, it could hint at a wormhole. There's also the possibility of catching exotic emissions. Consider that a wormhole connecting 2 different environments might have matter flowing through. Imagine one mouth is near an active galactic nucleus with hot gas and radiation, and the other mouth is in a quiet galaxy. We might see high-energy particles suddenly appearing from empty space near the quiet galaxy's mouth, basically stuff shooting out of nowhere from the perspective of that galaxy. This could look like a spherical outburst or an unusual radiation source with no obvious power supply. Some astrophysicists speculated that certain unexplained phenomena could, with a lot of imagination, be wormholes. One example, the so-called odd radio circles, AURCs, discovered in recent radio astronomy surveys, giant ring-like radio emissions in the sky with no clear counterpart in visible light. They are likely shock waves from galaxy interactions or remnants of some burst. But one hypothesis was, maybe it's a wormhole's sphere of influence. In that interpretation, a wormhole might cause a spherical wave of radiation, say from matter colliding as it enters a mouth, which we'd see as a circle, since we see the cross-section of a sphere from far away. This idea is very speculative, and AURCs are still under study with more mundane explanations, but it shows people are thinking about how wormholes could manifest. Another potential sign, gravitational waves. If two black holes collide and merge, LIGO and other detectors can catch the resulting gravitational wave signal. If wormholes exist, especially if they can form or oscillate, they too could emit gravitational waves. For instance, if a wormhole oscillates, the two mouths moving relative to each other like a spring, it would radiate gravitational waves. Or if something falls through a wormhole, the throat might vibrate and emit a burst. These signals might have distinctive echoes. Some theoretical work suggests that if black holes have interior wormhole structures or other exotic compact structures, after the main merger signal, there might be a series of faint echo pulses as gravitational waves bounce around inside the structure and leak out. Scientists have looked for unexplained echoes in LIGO data. There have been tentative claims, but nothing conclusive. Most in the field treat those with caution. Still, as detectors improve, gravitational waves could either reveal surprises or put tighter limits on exotic objects like wormholes. One more arena, the cosmic microwave background, CMB, the afterglow of the Big Bang. If a wormhole formed in the early universe, more on that soon, and it was large, it might have left an imprint on the CMB's patterns. Perhaps a strange symmetry or repetition. For example, seeing the same galaxy or cosmic feature in two widely separated areas of the sky because a wormhole made light paths converge. Cosmologists have searched the CMB for odd correlations, like matching spots or circles, that could indicate the topology of space is weird. Say, space is connected in loops, which would also cause duplicate patterns. None have been clearly found at a significant level. However, they usually weren't explicitly looking for wormholes, more for wraparound universes. A wormhole imprint would be a bit different and harder to differentiate from random fluctuations. It's a long shot, but an interesting one. If wormholes were abundant, we arguably might have noticed something by now. An unexplained lens here, an odd motion there. The fact that we haven't may suggest that if they exist, they are either extremely rare or very well hidden, for example, microscopic, or masquerading as black holes almost perfectly. On the other hand, our observational tools have only recently become precise enough to even contemplate these subtle effects. The orbits of stars at the galactic center, for instance, can now be measured with accuracy down to a fraction of a percent. In the coming decades, any tiny anomalies might start to surface. To summarize, scientists are actively scanning the heavens for unusual gravitational lensing signatures, double rings, unexplained multiple images, watching motions of stars and gas for perturbations that don't fit known masses, monitoring high-energy or transient events, gamma-ray bursts, radio bursts, cosmic rays, for patterns that could hint at matter coming or going mysteriously, listening with gravitational wave detectors for something weird that might point to exotic objects like wormholes, checking the cosmic background for patterns that defy conventional cosmology. So far, nothing has shouted wormhole here, but the search has really only begun. It's akin to looking for a needle in a haystack when you're not sure there even is a needle. But as technology and surveys improve, we might at least constrain the possibilities. For example, we could say, No wormhole bigger than X is present within Y light years, or we'd have seen effect Z. Even that is useful, as it tells theorists what's off the table. Now, beyond trying to find a wormhole, there's a deeper line of inquiry. Could wormholes have been formed naturally at all? We touched on the Big Bang and primordial wormholes. Let's explore that avenue. The possibility that wormholes are as old as the universe, forged in the furnace of creation itself, and perhaps still lurking in the cosmic wilderness. Primordial gateways, wormholes from the early universe. The idea of wormholes often leads to a natural question. If they can exist, could some have been formed in the early universe? Moments after the Big Bang, the cosmos was incredibly hot and dense, a roiling sea of energy and quantum fluctuations. Some theorists have suggested that in this initial quantum chaos, tiny wormholes might have spontaneously appeared and vanished as space itself foamed at the smallest scales. This concept of quantum foam, championed by physicist John Wheeler, imagines space-time at the Planck scale, the very smallest scale, as an ever-changing landscape where little tunnels and bubbles constantly form and dissolve. Most of these would be ridiculously small and fleeting, but what if one somehow got caught in the expansion of the universe? According to inflation theory, our universe underwent a brief period of explosive expansion, fractions of a second after the Big Bang. If a wormhole, even a submicroscopic one, popped up during that epoch, the rapid stretching of space could have blown it up in size as well, potentially to macroscopic proportions. Such a primordial wormhole would be a relic of creation, a carryover from the universe's birth. Unlike wormholes formed by the collapse of stars, which we have no evidence for either, these would be fundamentally ancient structures, predating galaxies and stars, threading through the cosmos from its infancy. What would happen to these wormholes over time? The universe's expansion might pull on them, or they might drift, anchored to nothing in particular. Many might have collapsed quickly if they weren't stable. The violent conditions of the early universe could destroy fragile structures. But some could theoretically survive to the present day, hidden in the vastness of space. They might be very difficult to distinguish from a small black hole gravitationally, unless we notice the peculiar signatures, like the unusual lensing effects or leakage of gravity to another region, discussed earlier. If one exists within our observable universe, it could connect extremely distant regions that were once close together at the Big Bang. Notably, Stephen Hawking and others speculated on the role of such primordial wormholes. Hawking mused that tiny wormholes might constantly be appearing and disappearing at the quantum level, and although most would be too unstable or too short-lived for any use, they hint that space-time is not a smooth sheet, but a restless ocean of possibilities. If inflation magnified a few of those fluctuations, then wormholes may be as much a part of the cosmic fabric as the galaxies and stars, just far harder to detect. Some researchers have even considered whether primordial wormholes could be linked to mysterious phenomena, like certain unexplained cosmic signals or the seeding of large-scale structures. But as of now, these ideas remain conjecture. In practical terms, if primordial wormholes exist, they offer a tantalizing opportunity. Nature's own wormhole laboratories scattered in space. We wouldn't need to create a wormhole from scratch if we could find and capture one. An advanced civilization might hunt for these ancient tunnels, trying to stabilize or enlarge them for transport. It sounds fantastical, but so does the entire wormhole concept. At the very least, the possibility of primordial wormholes reminds us that wormholes could have cosmic origins. They might not just be science fiction or theoretical solutions on paper, but real artifacts of the universe's birth, waiting eons in the darkness for someone to discover their entrances. Beyond light speed, communication and consciousness. Wormholes aren't just about moving people or ships. They also redefine how we might send information. In a universe without wormholes, no message can travel faster than light through normal space. which means a radio signal to a star 100 light-years away takes a century to arrive. But with a wormhole, communication could be essentially instantaneous, no matter the distance. Imagine a network of wormholes linking far-flung planets. Colonies across the galaxy could speak with each other in real time, sharing knowledge and culture without the tyranny of light-speed delays. It would be the ultimate communication infrastructure, an interstellar internet, where the ping times are zero. The implications for memory and data transfer are profound. A library's worth of data could be sent through a wormhole as easily as passing a book through a door. Archives light-years apart could effectively merge into one. One could back up information in a distant, safe location with no delay, providing security against local disasters. Even more striking is the prospect of consciousness travel. While physically moving a person requires transporting their body, one could imagine a scenario where a mind is copied or transmitted. With wormhole communication, perhaps in the far future, a person's neural patterns, their memories and personality, could be sent to another planet and downloaded into a waiting clone or robotic avatar. This would be a kind of teleportation of consciousness. You wake up on the other side of the galaxy in a new body, without your original body ever making the journey. It's speculative, but wormholes make the physical distance the least concerning part of that wild idea. Even without such advanced biotechnology, wormholes could allow something akin to telepresence on an unprecedented scale. Remote exploration robots on an alien world could be controlled in real time via a wormhole link, as if the operators were actually there. Surgeons on Earth could operate on patients in a spaceship light-years away by manipulating instruments through a small wormhole window. Friends separated by vast distances could virtually sit in the same room via a tiny wormhole portal, more intimate than any video call, because light and sound would actually be passing through a shared space. All of this hinges on having wormholes to use, of course, and it raises interesting physical and philosophical questions. Information going through a wormhole bypasses the normal route through space, but it still must obey consistency. One couldn't use a wormhole network to send a message to one's own past unless a time-offset wormhole was set up, with all the paradox issues we explored earlier. Engineers of a wormhole communication grid might have to enforce rules, for instance, preventing any wormhole pair from becoming a potential time loop communicator. But within those constraints, the benefits are staggering. The concept of transferring consciousness also forces us to ask, what is the self? If a mind can be projected elsewhere and inhabit a new vessel across the cosmos, are we more than our physical forms? Wormholes won't answer such philosophical queries directly, but they could provide the stage to test them, a way to separate mind from original matter without the gulf of space and time in between. In a way, wormholes might someday let us bridge not only space, but the gap between minds, connecting intelligences across distance in a form of direct communication that makes current technology look like smoke signals. These possibilities exemplify how wormholes, if harnessed, would revolutionize civilization. They collapse not just space, but also the separation between beings. With instant communication and the potential exchange of thoughts or even selves, the universe would feel a great deal smaller and more intimate. It's a future in which distance is no barrier to sharing knowledge or love. A future where the saying, "we're all connected," is physically, literally true. Gateways and guardians, the ethics of wormhole use. If wormholes become a reality, humanity, or any intelligent users, will face serious ethical and security dilemmas. The power to bridge star systems or centuries comes with responsibilities that dwarf those of previous technologies. One immediate concern is control. Who gets to use a wormhole and who decides where and when it leads? A traversable wormhole, especially the first of its kind, could be the most coveted asset in history. Governments, corporations, or other groups might struggle for monopoly over these gateways. After all, controlling a wormhole is like controlling a shortcut through space and time, a strategic high ground unparalleled in significance. We can draw parallels with past innovations. Consider when humans first built ocean-going ships. Trade routes and choke points became sources of immense power for empires. A wormhole route is even more absolute. If you control the only bridge to a resource-rich star system, you essentially control that system without needing a fleet. This suggests that unregulated wormhole use could lead to conflict. Nations might go to war over wormhole access, or a powerful entity might keep a network of wormholes secret to maintain an advantage. To prevent such outcomes, society would need frameworks, perhaps treaties that declare wormholes a common good, or international interplanetary bodies to supervise their operation, a bit like how we treat Antarctica or outer space in current international law, but with even higher stakes. There's also the question of security and misuse. A wormhole can be a doorway for commerce and travel, but also, potentially, a conduit for invasion or catastrophe. An enemy could send troops or weapons through a wormhole, bypassing all traditional defenses. Even a small wormhole could be used maliciously. Imagine someone opening a tiny wormhole in the middle of a city and funneling dangerous substances or deadly radiation through it from a safe distance. On a cosmic scale, one could theoretically divert matter from a star, like a stream of plasma, through a wormhole to threaten another world. Such scenarios mean that if wormholes exist, there may need to be agreements or technologies in place to police their usage, much like nuclear materials are monitored today. Wormhole detectors might be developed to alert if an unauthorized portal opens in a protected area, for instance, or fail-safes to collapse wormholes if misused. The time travel capability complicates ethics even further. If a wormhole network allows forward and backward time jumps by virtue of relativistic transport of one mouth, how do we handle the possibility of altering history? It might become necessary to establish strict laws, e.g., a prohibition on turning a wormhole into a time machine, perhaps enforced by international accord or automatic fail-safes in wormhole generators. One could imagine a chronology protection agency, a nod to Hawking's chronology protection conjecture, either a literal task force or simply the collective agreement of scientists to avoid creating causality paradoxes. People could be tempted to use wormholes to go back and prevent tragedies or gain advantage. Lottery numbers, anyone? Which raises moral dilemmas. Do we allow controlled, consensual changes to history? Or is any change a violation of the rights of those who lived through the original timeline? Most thinkers suspect that unrestricted time travel would be destabilizing. Thus, ethically, it might be near universally outlawed, even if physically achievable. Beyond overt misuse, there's the matter of equity. If wormholes are expensive or hard to make, initially only a rich elite or powerful governments might have access, widening the gap between those who can cross the stars and those who cannot. There will be ethical pressure to democratize such technology, to avoid a universe where a few get to gallivant across space-time while others are stuck on their homeworlds. History has shown that with airplanes, telephones, and the internet, widespread access eventually became key to unlocking the full benefit of the technology. Perhaps wormholes would follow a similar path, from military or elite use to general public utility. Still, ensuring fair access would be a challenge, requiring conscious effort. Finally, consider the environmental and existential risks. Every wormhole manipulation is an interference with space-time structure. Could creating or using wormholes have unforeseen side effects, like triggering that vacuum decay scenario or disrupting orbits? Ethically, we'd need to weigh the potential harm of tearing space-time against the benefits. It might be akin to early atomic scientists worrying about setting the atmosphere on fire with a nuclear test, an extremely low probability event, but with annihilating consequences if it came true. Responsible science demands we assess these risks honestly. Perhaps initial wormhole experiments would be done far from Earth, in case something went awry, or on a small scale before scaling up. In summary, wormholes would demand a new ethical framework. We'd need a blend of caution, international cooperation, and forward-thinking regulation to use them wisely. Much as the world came together, however imperfectly, to prevent nuclear war and to manage space resources peacefully, a similar or greater unity might be required to handle wormhole technology. The goal would be to maximize the wondrous benefits: quick travel, instantaneous communication, cultural exchange, while minimizing opportunities for disaster or domination. Achieving that balance could be one of humanity's greatest ethical tests, essentially asking, can we wield the power of the gods without succumbing to our very human flaws? Handled wisely, wormholes might even open pathways to domains utterly foreign to us. Among the wildest possibilities is the idea of connecting not just different regions of our universe, but entirely different universes. Across the multiverse, bridges to parallel realities. The word universe used to mean everything that exists. But modern cosmology and quantum theory have opened the door to the idea that our universe might be just one of many, a multiverse. If so, wormholes might not limit themselves to connecting points within one universe. They could, at least in theory, link different universes altogether. What do we mean by different universes? There are multiple concepts. One is the idea of separate bubble universes. Eternal inflation, a cosmological theory, suggests that as our universe inflated, other regions could inflate separately, creating bubble-like universes that are causally disconnected from ours. Normally, nothing can pass between bubble universes, but a wormhole might thread one bubble to another, like a tunnel between two separate soap bubbles. Another concept is brain worlds, which we touched on. Our universe could be a 3D brain floating in a higher dimensional space, and there might be other brains, other 3D worlds, parallel to ours in that higher dimension. Under the right circumstances, perhaps a wormhole is actually a tube through the higher dimensional bulk connecting two brains. If you stepped through, you'd literally leave our cosmos and emerge in a separate 3D universe with its own content. Yet another notion comes from quantum physics, many worlds interpretation, which posits that every quantum event that has multiple outcomes actually splits the universe into multiple branches, essentially parallel timelines or universes where each outcome occurs. Normally, those branches do not interact. They're like separate tracks of reality. But some speculative discussions wonder, could a wormhole allow travel between these quantum branches? This is a more exotic and controversial idea, but it's a staple of science fiction. The idea of alternate histories where, say, a wormhole could let you visit a world where the dinosaurs never went extinct or where a different outcome of history occurred. If wormholes can connect parallel universes, the possibilities are as vast as the imagination. You could have a shortcut, not just to another galaxy, but to an entirely different reality with different initial conditions, maybe even different physical constants. Some theoretical physicists have played with models where a wormhole connects a universe that has, say, a different value of the electromagnetic force. Stepping through might mean entering a realm where atoms are of a different size or stars burn at different rates. That sounds dangerous, and it would be, but it shows how far one can extend the mathematics. There is even a theory that black holes could be wormholes to new universes. One proposal is that when matter collapses into a black hole singularity, perhaps quantum gravity saves the day by avoiding an infinite crunch. Instead, the collapsing matter tunnels through a wormhole-like process and pops out as a new Big Bang in another universe. In this picture, every black hole might be an embryonic universe internally. If that were true, we don't know, then our universe's own Big Bang might have been born from the interior of a black hole in some parent universe. It's a mind-bending idea. Wormholes as the umbilical cords of baby universes. Now, have we any evidence of anything beyond our universe to even hint at wormholes connecting universes? Not really. By definition, other universes, if they exist, are not observable except by perhaps subtle gravitational effects, or if a wormhole gate exists. There have been claims of unexplained cold spots in the cosmic microwave background that some attributed to a collision with another universe's bubble, but those interpretations are speculative. If a wormhole connected to another universe, how would we know it's another universe and not just another part of our universe? One clue might be if something impossible appears through it, say stars or particles that don't match what our universe's physics allows. Perhaps the chemical composition is weird, or physical constants measured through the wormhole region seem off. If you stuck a probe partially through a wormhole and noticed that on the far side pi calculated differently, or the spectrum of hydrogen was shifted, you might suspect you're not in Kansas or this universe anymore. Why entertain such extreme ideas? In part because modern physics has extreme ideas on the table anyway. Multiple dimensions, many worlds, etc. Wormholes are already exotic, so connecting them to other exotic frameworks is natural for theoretical exploration. And philosophically, it's alluring. Wormholes as a tool, not just for spacefaring, but for multiverse exploration. Civilizations might not only spread across their own galaxy, but hop to entirely different universes, effectively making them inter-universal travelers. It's the ultimate frontier. From a story perspective, it raises stakes and puzzles. If wormholes can connect universes, then somewhere out there could be an alternate version of you, and a wormhole could bring you face to face. Or a universe where life never arose might be colonized via a wormhole by life from our universe. One could contemplate a network of wormholes linking a meta-universe of many worlds. Now, scientifically, this remains in the realm of speculation. We have no evidence of other universes, and wormholes themselves are unproven. So a wormhole connecting universes is speculation squared. But it's a healthy exercise in pushing limits. It forces us to clarify what we mean by universe and space-time. If nothing else, thinking about multiverse wormholes brings us back to the philosophical. What is reality? If wormholes let us step outside our known reality, does that change our perspective of our place in existence? Perhaps in confronting the multiverse, we realize how precious our particular home universe is, or conversely, how small it is in a larger ensemble. One practical consideration. If a wormhole can connect two universes, can it disconnect? If that wormhole closes while you're in another universe, you could be truly stranded, with no realm of existence to return to. The bravery, or folly, of stepping through a wormhole to an entirely different reality is immense. As we come to the end of our speculative trek, it's fitting to turn reflective. Wormholes, real or not, force us to re-examine our notions of distance, time, and separateness. They are a mirror to our desires and our fears. What would it mean for beings like us to have such power? What would it do to how we see distance, presence, causality? This leads us into the philosophical domain, reconsidering fundamentals like far and near, and reflecting on the human condition in light of these cosmic possibilities. Rethinking reality. Philosophical implications of wormholes. The mere possibility of wormholes compels us to re-examine some deeply held intuitions about space, time, and our own lives. Distance and space. We normally think of space as something that guarantees separation. If two cities are 1,000 miles apart, that distance is an obstacle. It implies travel time, effort, maybe the impossibility of daily interaction. On cosmic scales, distance becomes almost synonymous with isolation. Galaxies are millions of light years apart, effectively meaning we cannot interact within any human timescale. Wormholes, if they exist, break that notion. They suggest that distance is not an absolute barrier, but a malleable dimension that can, in principle, be folded or pierced. If you can step through a wormhole and be 1,000 light years away in a second, then far and near cease to have the same meaning. The emotional weight behind distance, the sense that loved ones are irretrievably far or that a place is out of reach, would be profoundly changed. Wormholes would make the universe, even the multiverse, feel that much smaller and more connected. This echoes, in a philosophical way, the idea from quantum entanglement that maybe all points in space are secretly tied together. With wormholes, that would be literally true for the points they link. Presence and location. If wormholes allow essentially instantaneous relocation, what does it mean to be here or there? We might become entities that exist effectively in multiple places in short order. You could wake up on Earth, have lunch on a planet orbiting Vega, and be home by evening. Our sense of home might expand to include multiple worlds. Presence becomes a choice, not a fate determined by where you were born or where you currently stand. In a sense, wormholes could liberate us from geography. On a deeper level, it makes us ask, is location an inherent property or just a temporary condition? If you and I can meet physically despite living galaxies apart, then distance truly becomes a state of mind, almost an illusion broken by knowledge and technology. Consider also identity. Throughout history, communities have been shaped by who can physically meet whom. Wormholes would scramble that. You could form a community of beings from different star systems who meet daily in a common space via wormhole. This would challenge cultural and personal identities to broaden. Earth-based identifiers might seem trivial when your best friend is from a planet 50 light-years away. Philosophically, one might argue wormholes make us realize the triviality of physical distance in defining relationships or communities. Causality and time. Wormholes blur the clear arrow of time if used improperly. This forces a philosophical stance. Perhaps the universe has a strict rule, no going back and altering things, as Hawking humorously said, to protect the historians. Or perhaps the universe is okay with loops and multiple timelines. If wormholes allowed time travel, we'd confront the paradoxes we discuss not just as abstract, but as ethical and existential issues. Could you maintain a coherent sense of self if your personal timeline is no longer linear or unique? What becomes of responsibility and causality if effects can precede causes via a wormhole shortcut? Some philosophers suggest that if time travel, via wormholes or otherwise, were possible, free will might be an illusion, or the universe might be a block where everything is predetermined to avoid paradox. Or if multiple timelines are created, then every possible choice is made in some branch. Again, challenging the idea of personal responsibility or unique identity. You exist in countless variants. Even without time travel, wormholes shorten cause and effect delays. A supernova that would have taken 100,000 years to affect us via normal space, like sending a shockwave or cosmic rays, might, through a wormhole connection, affect us immediately. That entangles distant events with local ones in a way that upends our usual causal order. Cosmic events usually play out on timescales safely separate from human ones, but wormholes change that. Travel without moving. This phrase, popularized in fiction, like the spice navigators in dune-folding space, or mysticism, becomes almost literal. Wormholes allow one to go somewhere without the journey in between. Philosophically, journeys have been metaphors for personal growth. It's not the destination, it's the journey, people say. If the journey is instantaneous, do we lose something? One could worry that eliminating travel, the process, might cheapen the experience of reaching a destination. On the other hand, one could argue that we find meaning in what we experience, not how long it takes. Wormholes might force us to find new ways to gain the perspective and growth that travel over time and space used to provide. Perhaps with the drudgery of transit gone, we'd spend more time truly engaging with new places or peoples. It also raises Zen-like questions. There's a well-known koan, without moving, you arrive. Wormholes make that concrete. It challenges the primacy of physical movement in our conception of progress or adventure. You could cross the universe by taking a single step through a portal. It's very anti the classical heroic journey, which is full of trials. Does that make the universe less grand if it's so easily crossed? Or does it simply remove the barriers so we can focus on what truly matters: knowledge, connection? The unity of space-time. Einstein already unified space and time conceptually. Wormholes, in a sense, unify separated spaces and potentially separated times. They bring far-flung corners into contact. Philosophically, this resonates with ideas of underlying unity, that all things are connected. Many spiritual traditions speak of oneness, that separateness is an illusion. Wormholes would be a literal manifestation of that principle. For certain points, the distance is zero. If one embraced that metaphor, you might say wormholes show us that the universe is deeply interconnected in ways our senses did not initially reveal. Perhaps what we perceive as empty space between objects is not a forbidding void, but something that can be bridged by understanding nature's hidden dimensions. Human meaning and purpose. Since time immemorial, part of the human condition has been coping with separation. From each other, distance, from places we care about, even from times, the past, future. We've invented telephones, airplanes, the internet to mitigate these, but wormholes would nearly eliminate them. What then? Some might fear a loss of challenge. If you can go anywhere or anywhen, what do you long for? Others might say it allows us to focus on higher goals now that basic separation is solved. It also touches the existential longing. Are we alone? Wormholes, if they allowed meeting aliens easily, could fill the universe with neighbors. But then, the specialness of Earth might diminish, or we might feel less unique, which is both humbling and potentially troubling if we define ourselves by our uniqueness. Ultimately, wormholes bring to life the phrase, annihilation of space and time, something early telegraph users in the 19th century marveled at when messages could outpace horses. With each leap, trains, planes, radio, internet, we've had to adjust our philosophical and societal outlook. Wormholes would be a leap orders of magnitude greater. It would force a kind of cosmic cosmopolitanism. The Earth could be as connected to a planet in Andromeda as New York is to London today. The psychological impact could be huge, perhaps expanding our empathy to truly cosmic scales, or causing a kind of culture shock as humanity, or any species, faces a radically enlarged scope of life. One can also ponder, if wormholes allow us to be effectively everywhere, do concepts like frontier or exploration lose meaning? Part of our drive comes from things being difficult to reach. If everything is reachable, do we become complacent? Or do we find new frontiers in realms of knowledge, art, internal consciousness? Probably the latter. We shift from physical exploration to exploration of ideas or creativity. The external frontier might become the internal frontier. In embracing wormholes, we would be taking on what once were attributes of gods: omnipresence, being anywhere quickly, and perhaps even some form of immortality or time manipulation. Philosophers and theologians might have much to say about humans stepping into those shoes. Is it hubris or fulfillment of destiny? Are we playing God by rearranging space-time, or are we simply utilizing the tools the universe gave us? As we reel from these profound thoughts, it's clear that wormholes, whether real or not, function as a splendid mirror. In them, we see reflected our eternal desire to not be bound by limits, not by distance, not by time, not by isolation. They encapsulate our refusal to accept that the stars are beyond reach or that the past is forever gone. Wormholes are, in a way, the scientific analogue of hope and imagination, an insistence that somewhere, somehow, there must be a way. And so we come full circle to the human heart of this matter. Why do we yearn for wormholes? Because, at root, they represent connection, the defeat of cosmic loneliness. It's fitting then to conclude by returning to that emotional core, reflecting on how, through love, curiosity, and indomitable will, we strive to forge connections that even space-time cannot tear apart. Beyond all distance, the human drive to connect. From the moment early humans first climbed a hill and wondered what lay beyond the horizon, we have been a species of explorers,
and bridge builders. We crossed oceans with fragile ships, traversed continents on foot and horseback, and eventually soared through the skies in airplanes. Each time we encountered a horizon, we found a way to reach beyond it. The greatest horizon of all has been the sky above, the vastness of space and time. Wormholes represent the ultimate bridge, the final answer to the challenge of distance. Why do we care so much about bridging distance? It's not just curiosity, though that is a powerful engine. It's also something profoundly emotional. We seek to not be alone. We yearn to connect with others, to see and touch the places that inspire us, to ensure that nothing, not even light years of emptiness, can keep us apart from what we love or desire to know. Think of the loneliness of a spacecraft drifting between stars, decades from any signal. Now imagine that isolation erased by a shortcut. A crew steps through a wormhole and instantly finds themselves greeted by the light of a new sun and the faces of colleagues who went ahead. That moment would be transformative, a triumph over what once seemed an iron law of nature. It would say, we refuse to accept separation. Throughout this script, we've danced between cold equations and poetic visions because wormholes demand both. The science might one day allow or disallow them, but until then, they live in our collective imagination as symbols of ultimate possibility. They whisper that maybe, just maybe, the universe is kinder than it looks, that the great distances that keep us apart might be circumvented by intelligence and perseverance. Consider a future where wormholes are real. A grandmother on Earth could hug her granddaughter on a colony light years away and be home by evening. Scholars could walk through a library wormhole to consult archives on a planet in another galaxy. Friends separated by time could, through the careful use of a wormhole, meet again at a chosen moment. These are almost utopian scenarios, of closeness regained, of knowledge unbounded. And yet they spring from the same fundamental human motivation that sent explorers across uncharted seas and astronauts to the moon. The desire to reach, to connect, to understand. In a sense, wormholes, real or not, hold a mirror to humanity. They show that we are not content with walls and limits. If space has an end, we want to see what lies beyond. If there's a barrier, we feel an urge to bridge it. This refusal to be confined, this restless drive, is one of our defining qualities. It is the reason people first left their home valleys, the reason we send robotic emissaries beyond our solar system, and the reason we contemplate technologies as extreme as wormholes. Of course, any technology is double-edged. Control of wormholes would be an immense power. Who decides how they're used? Could they be weaponized? We touched on how it would require great wisdom and cooperation to use such power safely. But let's imagine that we rise to the occasion. That knowledge is guided by compassion and caution. In that case, wormholes could become arteries of empathy as much as commerce. Imagine not just exchanging goods, but ideas and cultures freely across light years. The galaxy, or galaxies, could become a tapestry of interwoven civilizations, each unique but connected. There's a poignant aspect too. If one day we master wormholes, what next? Will there come a time when every point in space we care about is accessible, and we'll look outward and find no place new to go? Perhaps then we'll turn inward, to the infinite spaces of mind and creativity, frontiers that can never be exhausted. Perhaps wormholes, by solving the external challenges of distance, will let us focus on exploring questions of meaning, purpose, and inner fulfillment. As we reach for these keys to the cosmos, we find ourselves living out the oldest dreams of our species. We have always imagined magic portals and celestial bridges, from the rainbow path of Norse myth to the flying chariots of Hindu lore, ways to connect realms separated by vastness. With wormholes, those age-old fantasies inch toward reality, rendered in equations and engineered apparatus. The line between myth and science blurs. We become,
in a sense, the bridge builders that our ancestors could only ascribe to gods, opening the gates of heaven, uniting worlds, transcending limits. These powers move from folklore to the laboratory. The challenges are monumental, but so is our collective will to overcome distance. In pursuing wormholes, we are propelled by the same force that once made us launch ships across uncharted oceans and send signals into the dark of space, the unyielding human spirit of connection. It is that spirit that will light our way as we strive to unlock nature's most wondrous back doors and step through into whatever lies beyond. The cosmos awaits. Perhaps not as a void to be feared, but as a home rich with rooms and hallways we have yet to walk. Our longing to traverse its depths is, in the end, a longing to fulfill our own potential. Wormholes or not, that spirit of connection will continue to guide us as we live out this grand story written in the stars, forging bonds that even the fabric of space-time cannot sever. As we reach for these cosmic doorways, we are echoing our oldest tales of secret passages to the heavens. But this time, we might hold the key in our hands. We find that the bridges we seek out there have been inspired by what is in here all along, our capacity to wonder, to strive, and to connect. For generations, we've told stories of magic portals and divine chariots bridging worlds. With wormholes, those narratives edge toward reality under the guidance of science. In building these gateways, we step into roles once reserved for the gods in our legends, opening celestial doors, uniting what was separate. And though the technical challenges are immense, our drive to connect is even greater. It will be the light that guides us through those cosmic doorways. In the end, the pursuit of wormholes is not just a scientific adventure, it's a celebration of the human spirit. It shows our refusal to be limited by distance, time, or even reality itself. Whether or not wormholes become a practical reality, the hope and determination behind them will continue to define us. We will carry with us all the dreams of those who dared to believe that no door stays closed forever. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light, really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery, a cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, Perhaps the shockwave from a distant supernova or a random density fluctuation causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens: ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars, which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core, for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now, and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth, and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc2. 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10^26 watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example, the star Sirius, the brightest star in Earth's night sky, is about twice the sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger, more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the sun might emit thousands of times more energy, blazing a brilliant blue, white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the sun's mass, this red giant stage is essentially the beginning of the end. After perhaps 1 billion years in the red giant phase, the sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the sun's shed gases will mix into the interstellar medium, enriching it with elements the sun made.
All that remains of the Sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our Sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1 million times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint, white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade.
Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star. But once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. A powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant, composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, carbon, oxygen, calcium, iron, gold, and so on, are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our Sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly. Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1. Half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium. And here, the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late-generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars.
In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue,
Imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, they were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly a billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way, stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution, myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if starbirth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our sun. but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun-like stars have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually inspiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our Sun stands alone. Yet the Sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The Sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the Sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the Sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our Sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension, and yet the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun, like stars, harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun, like star with an Earth-ish planet, might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways.
Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares.
Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon indicating that galaxy's distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point. By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young. but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of 2 white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths, stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the larger scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars.
to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns.